Hooke's law states that the force needed to extend a spring by some distance is equal to the spring constant times that distance, which is the force is equal to the spring constant times the distance, or the force divided by the distance is equal to the spring constant. My first spring is made up of hair ties. It is the least stretchy and has the lowest spring constant. To calculate the spring constant, I divided the distance from equilibrium by the force pulling down. My second spring was made up of small elastics tied together. This spring was slightly more stretchy than the first. The spring constant ended up being 0.0134. My third spring was made out of more small elastics. There was many more elastics this time, making it a lot more stretchy. The spring constant ended up being the largest, which was 0.0364. All three springs were tested with the same force, which is how I solved for their spring constants. The last two were the same material, just more of it. The third spring showed that the more of the same spring you have, the larger the spring constant. I used my second spring to see if changing the amplitude changed the period. All of the periods ended up being the same. The bouncing was different because on the longer amplitudes, the bouncing was faster because of the longer distance it has to travel, and on the shorter amplitude, the bouncing was slower. Even though changing the amplitude appears to change the period, it in fact does not. Next, I compared masses to the period. The period of the heaviest object was 0.73 seconds. The period of the middle object was 0.71 seconds, and the period of the smallest object was 0.69 seconds. Even though the mass does have a take on the period, since all of these masses were pretty close together, you can't see a huge difference in the periods. Next, I evaluated whether spring constants affected the period. With my hair tie spring, this period was 0.3 seconds. With my extra long elastic spring, the period was 1.23 seconds. And with my short elastic spring, my period was 0.64 seconds. It turned out that the larger the spring constant was, the longer the period was. The length of a pendulum is directly related to the period. When the length was 0.18 meters, the period was 0.93 seconds. When the length was 0.34 meters, the period was 1.3 seconds. When the length was 0.5 meters, the period was 1.44 seconds. Next, I compared different masses and their periods to see if a change in mass affected the period. I tested 3 very different masses, and all of them had the same period of about 1.3 seconds. By changing the amplitude, I discovered that the amplitude does not affect the period. With a small amplitude, the period was 1.2 seconds. With a medium amplitude, the period was 1.19 seconds, and with a large amplitude, the period was 1.19 seconds. So no matter what the amplitude is, the period will stay the same.